So hi everyone, in this demo lecture we'll have a look at multiple sequence alignment. So the outline for this course is, first we will implement the optimal algorithm for multiple sequence alignment, which is the dynamic programming algorithm. Then we'll see why in practice we need heuristics for the real world data in bioinformatics. And then finally we'll have a look at the heuristic algorithms that are used in practice. One heuristic algorithm that we'll use is ClustalW. We'll use 6 protein sequences to align using this ClustalW alignment tool. Then we'll understand the alignment in detail and what are the features of this tool and how we can tweak according to our needs. Okay. We have this recurrence relation. We have seen this recurrence relation in our previous lectures. This is for alignment of 2 sequences. We have a similar recurrence relation when we have 3 sequences as well. So it's just that when we have 3 sequences, the number of cases to fill in each cell of the dynamic programming table increases exponentially. In case of 2 sequences, it was 2. In case of 3 sequences, it's 7. So in case of 2 sequences, it was 3. In case of 3 sequences, it's 7. Okay. So let's have a look at the dynamic programming algorithm. Okay. So I have already implemented the dynamic programming algorithm for alignment of 2 sequences. You have already seen this recurrence relation. And this is the dynamic programming algorithm for 2 sequences. First you just calculate the length of 2 sequences, just write the base conditions, and then you just loop through all the cells of dynamic programming table, and this is the traceback code. So we'll write a similar code when we have to align 3 sequences. Only differences we would see is that here we had just 3 conditions, there would have 7 conditions. In traceback as well, here we have 3 conditions, there would have 7 conditions, and so on. Okay. So let's start our dynamic programming code. Let's first take 3 variables to calculate length of 3 sequences, sequence 1, length of sequence 2, and then length of sequence 3. Okay, and then let's make our 3D dynamic programming table, initially filled with all zeros. Okay, range plus 1, range m n plus 1, and this m plus 1. Okay, so we have calculated the length of 3 sequences, build a 3D dynamic programming table which is initially filled with all zeros. Let's write our base conditions. So here let's first write our base condition when there are gap in 2 sequences, that is, let's write m plus 1, right, and here we'll have dp of I 0 0, that is, a gap is in both the sequences. Sequence 2 and sequence 3 there is a gap, in sequence 1 we are aligning the ith character. So for that case I'm defining a gap cost of using the SP score that you have already seen in previous lectures. So since there is gap in 2 sequences, a character in third sequence. So what happens is that when you align them pairwise, you will get a cost of 2. So let's multiply the cost of 2. Similarly, we'll have to do it for other 2 sequences as well. Let's do that quickly. Let's say 0 will be j cross. Again, the cost is 2. Similarly, let's do it for the third sequence as well. Okay, this is dp 0 0 k equal to k into 2. Okay, but actually that's not it. For base condition, we have to write here the second level of base condition as well, because when we were aligning 2 sequences, we just have to write base condition for the first row and the first column. But here, if you see, look at this cube, because here it's not a 2D table, it's a cube. So instead of in addition to writing the base condition for these lines, we have to write base condition for this plane and this plane as well. So let's write base condition for these planes. These base conditions are going to be very similar to the actual code that we wrote for a 2D alignment of sequences. So let's do the same. Okay. Okay, so for 2D alignment of sequences, we did this thing. So exactly we have to do almost the same thing. I can just copy the code from here and paste it here. The only difference that we'll have to do is here we have a 3D dynamic programming table. However, we are introducing a gap in third sequence. So let's just write this here. Yeah, and the third would be a gap, right? Similarly, here also the third sequence would have a gap character, and let's write this, right? And this also dp of ij and 0, right? So similarly, now we are introducing gap in the third sequence, and first sequence and second sequence will be aligning the characters, whatever the characters are there at I and j positions, right? So similarly, we'll have to do this for a sequence. Let's say we introduce gap in sequence 1, sequence 2 and 3 characters will align. So let's do that. Let's do that here. 1, 2 and plus 1. Similarly, okay, for k in range 1, 2, O plus 1. Right, we write similarly these conditions that dp 0, because we are not taking the first sequence, and then here j minus 1, k minus 1, plus we write the cost of aligning these characters. The first is the gap character, and then is sequence 2th, sequence 2 ith character, and sequence 3 kth character, sorry, not ith, jth character. Okay. Right. Similarly, in condition 2, it will be dp, let's say 0. Let's introduce gap in sequence 2 as well. Just take the alignment of sequence 3. Okay, this again gap in sequence 2. For sequence 3, we are aligning this k minus 1th character. Okay. Similarly, we can write third condition where we are introducing gap in first and third sequence, but aligning the character of the second sequence. Similarly, the gap cost, sequence 2, j minus 1th character, and sequence 3. Okay, for sequence 3 we have just gap, right? Okay, so similarly we'll have to do it when we have we are aligning sequence 1 and 3 character, introducing gap in sequence 2. So I already have this demo helper code with me. I'll just simply copy paste this code from there. Right. Okay. So all these 3 codes are almost very similar to each other. It's just that first time it's sequence 1 and 2, then sequence 2 and 3, then sequence 1 and 3, and so on. Okay. Now base conditions are done. Now it's time for the actual for loops, where we'll be implementing all these 7 conditions that we looked at in the recursion. So let's write those recursion. Let's write that recursion in range n plus 1 for j in range n plus 1. Okay, this is range. Then for k in for k in range O plus 1. Right. Again, this is range. Okay. So let's write those 7 conditions according to our recursion. So you see this recursion, we are going to write 7 conditions according to the same recursion. So let's write the first condition, that is dp I minus 1, j minus 1, k minus 1, that is we are looking at the diagonal cell, and okay, and then this cost, and in the cost function sequence 1 I minus 1th character, sequence 2 j minus 1th character, and sequence 3 k minus 1th character, right? Similarly, we write condition C2, where let's write this condition that we are introducing gap in sequence 3. So it's just k, and write cost, sequence 1 of I minus 1, sequence 2 of j minus 1 and just the gap character here. Okay, so we are writing coast here multiple times, but we have not defined our coast function yet. So we'll define our coast function shortly. Let's just write one more time. Just one more condition. Let's introduce gap in sequence 2 and align the character of this case. So we have to just write all these 7 cases one by one. So instead of writing all other 4 cases also one by one, what I'll do is I'll copy paste the other cases from here, from my helper code. Let me just copy paste these cases. Okay, so we have all these 7 cases: I minus 1, j minus 1, k minus 1, I minus 1, j minus 1 and k, I minus 1, j, k minus 1, all these cases that we have seen here, right? Okay, the next thing we do is, and we store this in dp ijk, that is ijk cell of dp, but the minimum of all these 7 cases, right? C1, C2, C3, C4, C5, C6 and C7 condition, right? Okay, so now it's our time to define this coast function that we have not defined. So let's define our coast function. Let's define coast function. It takes 3 characters, a, b and c. So like they can be a character of the sequence or a gap character, any of them. So the first case is, let's say if all of these characters are same, then we align them with a coast of 0, right? So we return 0. And if let's say 2 of them are same, if this is the case, or b equal to c, or this is the case that a equal to c, not 3 of them are same, then we return 2. Why 2? Let's say we have this case that a and b are same and c is different. So what happens is, when we align pairwise according to SP score, when we align a and b, we'll get a score of 0. When we align a and c, the score will be 1. When we align b and c, score will be 1. So the coast is 2, that we are returning the coast of 2. Else, if all of them are different, then the coast of aligning AB would be 1, BC would be 1 and AC would also be 1. So let's return 3 in this case. You can modify this code according to your needs. When there are 4 sequences or when there are m sequences, we'll have MC2 cases for this SP score, and just call this function that these 2 characters, what is the cost of aligning these 2 characters, and then finally add those all MC2 cases. Okay. So in this case, it's simple that we can simply write for align, if the 2 characters are same, then the cost is 2. If all of 3m are different, then the cost is 3. Okay. So this part is done. The next part is about traceback. So let's do traceback now. Okay. For traceback, it's simple. Let's again, so we know that we start our traceback from the, in case of 2D, we start from the rightmost, the down right corner of our table. Here also we'll start from MNO, a cell of our 3D cube, that is 3D dynamic programming table. So let's say that. And okay, also to get the aligned sequences, let's define these 3 variables: align sequence 1, align sequence 2, align sequence 3. They are all empty arrays for now. We'll append the characters as per our alignment. Okay, so let's write while I is greater than 0 or j is greater than 0 or k is greater than 0. That is we have not reached the 0, 0, 0 cell of our dynamic programming cube. So what we do is we again just do all those 7 cases. Let's say we look at the first case. The first case is we are checking that if we have reached the ijk from I minus 1, j minus 1, k minus 1, to check that this is just a sanity check, that if I is greater than 0, j is greater than 0 and k is greater than 0, if that is the case, then only we can go to I minus 1, j minus 1 and k minus 1. So that is just a sanity check, that is not a part of our condition. So let's write this: k minus 1 plus cost of, okay. So if we are going to I minus 1, j minus 1, k minus 1 cell, so it will be from, the cost will be coming from aligning sequence 2 jth character, sequence 3 kth character, and so on. Okay, one thing that you have noticed here is if you look at this recursion here, this is xi, yi, xi, yj and zk, whereas what we are doing is xi minus 1, yj minus 1, zk minus 1. This is because here it's just a pseudocode, but here we are aligning it based on, so we have built our DP and we have just filled our first row, first column and first third direction with zeros. So this is one indexing based, however the sequences are 0 indexing based, so just to adjust the indexing. Okay, see if that is the case, then we know that line sequence 1 we have to append sequence 1 I minus 1, line sequence 2 we have to append sequence 2 jth character, and in line sequence 3 we'll have to append sequence 3 kth character, right? And since we have reached to that particular cell, we'll also decrement I, j and k, right? Okay, that's done. This condition is done. What is the next condition? Let's write the next condition. Let's look at this code. Here we have written that in the next condition, let's look at the cell where the where the character of sequence 1 and character of sequence 2 were aligned, and in case of sequence 3 it was a gap. Let's look at that cell. If we have reached I, j, k using that cell, so let's look at that condition. We'll have to just check if I is greater than 0 and j is greater than 0, because k anyways is the gap character. I minus 1, j minus 1, this is k. Then we'll write cost of aligning sequence 1, sequence 2th character, and a gap here, right? And if that is the case, here what we did is that if from this cell plus aligning sequence 1, sequence 2 and sequence 3rd character, if it is equal to dp of I, j, k, sorry that was missing. If it is equal to dp of I, j, k, then we know that we have came from our dp I minus 1, j minus 1, k minus 1 itself. Here, if this is the case, that if this is the case, that using dp of I minus 1, j minus 1 and k plus aligning the sequence 1th ith character, sequence 2 jth character and gap character in case of sequence 3, if aligning these we have reached I, j, kth cell, in that case we know that align sequence 1 would have contained sequence 1 I minus 1th character, align sequence 2 would have contained sequence 2 j minus 1th character. Actually this j minus 1th character actually means the jth character, not j minus 1th character, because here we are just using 1 based indexing for dp, that's why. Okay, and in case of sequence 3 it would be just the gap character, and in this case we'll have to decrement I, j but not k, because for k we did not decrement, we just because we did not go to k minus 1 itself, we just go to I minus 1, j minus 1 and k itself, right? Okay, similarly you see there will be 7 conditions, so instead of writing all those 7 conditions here, I'll just import those 7 conditions from my helper code. So these first 2 conditions I have written, so let's copy paste all these conditions from the helper code. Okay, just a second. Okay, right, all right. Okay, copy pasted all other conditions from helper code. So these conditions, so like if this is coming from I minus 1, j minus 1, k minus 1 cell, I minus 1, j minus 1, k cell, I minus 1, j, k minus 1 cell, and so on, right? So now we have written all our conditions as well. So that's why we have reached, once we reach 0, 0, 0 cell of our dynamic programming cube, we'll get our aligned sequences. But since we started from the rightmost, down rightmost corner, we'll get the aligned sequences in reverse order. So let's just, let's just reverse them. So I will, for reversing, we'll just use a predefined function in Python, that is reverse, and we'll also reverse the align sequence 3. Okay. And so we have reversed all these sequences. We know our answer would be stored, that is the alignment score would be stored in dp of m, dp of m n o, right? Okay, and from this function let's return our dp, align sequence 1, align sequence 2, and our align sequence 3, right? Okay, so before we move on to test this code, let's see for any trivial mistakes in the code. Okay, I see here should be this starting from 1 instead of 0. Similarly here, instead of 0 it should start from 1. Anything else, it's starting from 1, it's starting from 1. Here also starting from 1. It should be min, not max. Okay, seems okay. Okay, I have already implemented this before for our helper function. So let's take this input sequences from our helper function, and let's write our input sequences. For now, let me just collapse this. Okay, all right, so let's run this code now. Okay, we get the alignment, and alignment score is 18. You see, we got the alignment very fast. So however, the sequence lengths are just 10 or 12. So let's look for bigger sequences. Let's copy this input. In this case, the sequences are of length around 150 to 200. Let's see how much time it takes for sequences of length 150 to 200. So it has already taken more than 5 seconds. Let's see. Okay, we got the alignment, and alignment score is 241. We got the alignment printed as well, but it took around 10 seconds. Even for the length of sequence length of around 150 to 200, imagine in real life in bioinformatics we have sequences of length tens of thousands and even to millions, and we do not just align 3 sequences. We align multiple sequences together of length 10,000s and millions, and that would take a lot time, because also this time is not scaling linearly. You see, when there are 3 sequences, it's a 3D table. When there are 4 sequences, it's a 4D table, and so on. And also the number of choices to fill in a particular cell are increasing exponentially, not linearly or quadratically. Since the increase in time complexity, since it's very computationally intensive, we use heuristic alignment tools. So there are multiple heuristic alignment tools. ClustalW is one of the heuristic alignment tools which uses progressive alignment heuristics, which we have already seen in our classes. So we'll use this ClustalW heuristic alignment tool to align 6 protein sequences and see the alignment in detail. So again, just a recap, what is progressive alignment? It's you just align sequences, 2 sequences at a time, and see what are the sequences that fits the best, and then align them. And then instead of m sequences, you are in sequences m-1 sequences, and again you do the same procedure and so on. So you progressively align first 2 sequences, then some other 2 sequences, and then finally, for example, in this particular case, we align these 2 sequences, then these 2 sequences, and then these 4 sequences, because after 2 steps these are just 2 sequences, and then finally all these sequences are aligned, and so on. To look at the ClustalW, let's go to ClustalW website. ClustalW. Okay, so this is a ClustalW program by GenomeNet. We'll use this program. So yeah, okay. In ClustalW, there are many output formats including Clustal, PIR, GD, FASTA. So we'll be using Clustal because it's more easily understandable format. Also, if you look at pairwise alignment, because I told that ClustalW uses progressive alignment heuristic, where in each step we do pairwise alignments. So for pairwise alignments also, we have option to use slow or accurate option, or just this fast or approximate. This fast approximate uses some other heuristics for pairwise alignment. Then slow and accurate is the dynamic programming algorithm. Also, you can even align protein sequences or DNA sequences. If DNA is the input, you can select DNA, otherwise protein. Also, you need not to copy the sequences here, you can choose the sequences from this file as well, and then execute multiple sequence alignment. There are other parameters as well. We will look at these parameters in detail later. First, let's go to Uniprot website to get 6 protein sequences. So we go to Uniprot. Okay. So here we can write either the protein name or the gene name. Let me write HBB, which is the hemoglobin subunit beta. So you see in hemoglobin, here is the entry name, here is the protein name, here is the gene name, which is HBB, and here the organism name. So this hemoglobin is present in different organisms, so all these organisms are listed here. And this is the length of the sequence, length of the protein sequence. Okay. Let's select 6 of the protein sequences from here. Let's select one is in human, this HBB in human. Let's select HBB in catfish. Also, let's select HBB in bovine. What else to select? Let's select from in giant panda. What other organism is interesting? Let's select in chimpanzee, because chimpanzee we know it's close to human. So let's see what the multiple sequence alignment says. Okay, others, let's select leopard. So we have selected 6 sequences. We'll click on this download button. Okay, compressed, no, we do not want compressed. You can also download, but you can also preview, and since these sequence lengths are very small, you can just directly copy those sequences from here. Copy, and let's go to our multiple sequence alignment, paste them here. Okay, once we get the multiple sequence alignment, this is the name, this is SP, this ID, and this HBB human. This will be used to refer to the sequence. So human is fine, bovine is also fine. Okay, the next one is, okay, here it's written SILAS, which we are not sure. Let's see what is the common name for SILAS. Okay, SILAS was catfish. So instead, let's write our common name. You can also modify these IDs. So instead of SILAS, I'll write catfish. And moving on, this is PNPO. Let's see, PNPO was which one? Okay, PNPO is leopard. So instead of PNPO, which is maybe a scientific name or ID, let's write leopard. And moving on, this is PNTR. PNTR is, okay, I see PNTR is chimpanzee. So instead of PNTR, we'll write chimpanzee. This is not necessary, but to understand the alignment later, it will be helpful. Instead of align, we'll write giant panda and we'll be done, right? Let's write giant panda. Okay, this giant panda is done. Okay, now we'll click on execute multiple sequence alignment to look at the, okay. So these are the 6 sequences. Here you see this is human, bovine, catfish, leopard, chimpanzee. These are the common names that we changed. So we can see them here. Then all the sequences are aligned, and the sequences that have the highest score. For example, here the highest score is 100, which is by alignment of sequence 1 and sequence 5. Sequence 1 is human, sequence 5 is chimpanzee. We already expected this, that human and chimpanzee will be aligned first. After that, other sequences will be aligned, their score will be calculated, and so on. This is a kind of tree that we have built, like first human and chimpanzee are aligned. To understand this alignment better and how these are aligned together, we can also look at the phylogenetic tree. There are multiple algorithms that construct phylogenetic tree. Let's just select tree menu, and we'll click on execute. And this, okay, the job is running. This will run in some time and we'll get the phylogenetic tree. And by phylogenetic tree, we'll get a better understanding how all of these different sequences are related to each other. For example, we saw human and chimpanzee are close to each other, so we expect human and chimpanzee to be aligned first in the phylogenetic tree and present on the same level, and after that they align to somewhere else. Okay, we have got the result. And if you look at this, human and chimpanzee, they are aligned first. No heterogeneity in these in terms of hemoglobin subunit beta. And then it is aligned to giant panda, and then finally it's aligned to leopard, then finally bovine, and catfish is far from each of these. So the length of this branches in phylogenetic tree also represents how heterogeneous these two are and how far related these two are. So if this branch is length is very large, then we see the catfish is far from each of these. Human and chimpanzee are close to each other, and then giant panda and so on. This is how we understand the alignment. You can also download the results from here. Okay, going back to here, we had to see about these parameters as well. So for fast and accurate k-tuple window size, if you know the approximate algorithm that is used here, you can set these k-tuple and window size accordingly. Here we know this accurate algorithm is the dynamic programming algorithm. We can set the gap open penalty, gap extension penalty, which weight metrics to use, whether it's BLOSUM, PAM, or IUB in case of DNA sequences. If it's protein sequences, you can select PAM or BLOSUM. BLOSUM is what we have selected. Also for multiple alignment, there are different parameters, gap open penalty, gap extension penalty, and so on. So you can leverage these parameters to according to your needs and get the alignment better. So thank you.